Hello, in this tutorial I'm going to show how to use vHelix to set up DNA nanotechnology systems for simulation in oxDNA sort of from scratch. And to do this I'm going to use a simple example of a classic DNA nanotechnology paper from 1998. But first I have to thank my sponsor, which is the EU, who funds my research. So thank you, EU. Okay, so the system that we're going to simulate today is this tile system from this very nice paper by Eric Winfrey and Ed Seaman from 1998, where they create a number of single-stranded DNA tiles that, when mixed together, form these large two-dimensional crystals that look fantastic. And since the individual tiles are very simple, they are a great system to get started with simulating oxDNA from vHelix. So there's a number of tiles, but the one I've chosen to demonstrate in this tutorial is this tile here. So to get started, we need Maya running the plugin vHelix. So when you see Maya like this, if you have the menu here called Helix, then you're running vHelix. And what I'm going to show here, it works best on the latest version of vHelix, which is unfortunately only available for Maya 2019 in Windows as of today. So the design aspects will work well in the other methods, in the older versions of Maya, but the oxDNA exporter only works correctly in the latest versions of vHelix, unfortunately. So what I'm going to do is, I'm going to, mostly for illustration, I'm going to import a picture of this tile. So I'm going to do this by using a Maya feature called image plane. So I'll do create free image plane. Now I create a little plane here. And what I can do is I can import an image. So I click here. Then I go to my tutorial folder, where I've basically just saved the picture of the tile from the paper I was just showing you. And I'm going to import it here. And this will just be a nice schematic for drawing. And here, of course, it's important to see that you're not looking through it backwards, because then it gets mirrored. So I'm pretty sure, yeah, this is the right side. So we can just have a quick look at this tile. It's basically built out of two parallel helices here that are, from the start, in their longest configuration, they are 42 nucleotides long. So that will be our starting material for our vHelix design of this. So we will create two DNA double helices. So I will go in here, helix, create helix, and select this little box here that allows me to control the length of the helix. And I'll just type in 42. So this will be our first helix. Okay, and now it's oriented opposite to the image plane, so I'm actually going to have to rotate the image plane. So I select image plane here, and then I click E on my keyboard to bring up this rotation menu here. And I'm going to select this green circle here and just rotate it like this so that it's parallel with the helices. And then I will click W to bring up these translation arrows to bring it in behind the helices. And this image plane is, of course, it isn't necessary. You can just as well have it on a printout or something. This image is just to show in this tutorial. And I'm also going to scale the image plane up a little bit to make it roughly as big as the helices. So to do that, I click R to bring the scaling menu up, and then I click the central square here and drag. So I hold and drag to scale it up so it's roughly as long as the helices. And now I'm going to select helix 1 and just bring it up. So this can be the top helix. And if you don't see, so this menu is super useful, and it's called the outliner in Maya. And this means that you can select the different things that you have inside your design. And if you don't see it, you click Windows Outliner to bring it up. And that will bring it up. So let's create our second helix. So I click helix, create helix, and I click the square here just to make sure that it's 42 nucleotides long. Yes. Then I create it, and now that it's been created, helix 2, I make sure to click W, so I have this translation menu with the arrows, and then I pull it down, so it's below the top helix. So it might seem natural that you want to get as tight a fit as possible between the helices, but what you will see in oxDNA is that it might be better to design things a little bit further apart than you would actually have them in the final design, because oxDNA has an easier time pulling things together that are far apart than pushing things apart. So it might be a good idea to design things that are topologically correct but a little bit more spaced apart than you would imagine them in your final design. So what I'm going to do now is actually apply the sequence of the DNA. So this doesn't have to be the first thing you do, but it makes sense in this design. And actually I'm going to have to pull the helices up and down a little bit so I can read what it says on my image here. So let's see. So I'm going to first apply this sequence here to the top helix. So I select the 5' end. So this 5' end here represents this yellow 5' end here. And I do helix, apply sequence, and that gives me a little prompt where I can enter the sequence, and I'm just going to read it here. So it's not super important that I get it correct in this example, but I'm going to try to do it right. TC ACT CT ACC GCA GG CAAA TG, and then the sequence follows up, continues up here. AGT CGA GGA C GGATCG. Okay. And now it automatically applies the complementary sequence to the paired bases on the other strand. And now I'm going to apply the sequence in the same fashion to the other strand. So here it gets a little bit tricky because actually on all helices we're going to have to trim off 5 nucleotides. So I'm just going to do it here first. I'm going to trim off 5 nucleotides from the 5' end here. So I'll select the first one and then click delete to remove it. 1, 2, 3, 4, 5 nucleotides. And then I can start applying this sequence here. I select the 5' end and do helix, apply sequence, and then I start adding this sequence that goes here. So it's CAT TCT GGA CG CCATA. If I mess this up, it doesn't matter that much. It's just an example. So GTC. So what we can check is was there sequence assigned to the last nucleotide? And yes, there was, but something got a little bit wrong here. So the last nucleotide should actually be a G. So I guess I messed up the sequence there somewhere. But it's just an example, so it doesn't matter. And then I'm gonna now continue to trim off all the ends of the helices to create these sticky ends that are in the design. So in this case here, I'm gonna trim off 5 nucleotides from the 5' end. That's 1, 2, 3, 4, 5, and I click delete every time. And then up here, I'm gonna trim off 5 nucleotides from the 3' end. So it's 1, 2, 3, 4, 5. And on this side, I'm going to trim off 5 nucleotides from the 3' end. So it's 1, 2, 3, 4, 5. And what's happened now is that there are some overhangs that never got a sequence here because it's not actually complementary to the main sequence that I applied before. So here we have 1, 2, 3, 4, 5 nucleotides that don't have a sequence, so we're just going to apply that now. So that's this sequence here, and we're going to have to read it backwards. So helix, apply sequence, G, A, G, A, G, A, T. Okay, now we sequence there. And likewise up here there is a overhang that doesn't have a sequence. So we select the 5' end, do helix, apply sequence, and now it's this sequence here. So it's C, A, T, A, C. Okay, so now all sequences should be applied in our design. So what we need to do now is design the crossovers between the two helices. You can see here and here. And I will just start now that they are far apart and just apply the nicks. So it's not necessary to apply nicks before you can just straightly do crossover straight away, but I'm just going to do it here for clarity. So what we have here is the strand that will be the yellow one here is the one that is gray here. So it's the protruding 5' end. And after 13 nucleotides, there will become a nick here. That will be the connection to the other's helix. So what I will do is I'll just count to 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think I hope I count that right. And then I select the one that I want to be the 13th, and I do helix disconnect bases. Now we create a nick downstream of the nucleotide. And then likewise here, this strand should have a nick after 13 nucleotides. Right. Yeah, I think so. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then I select the 13th nucleotide, do helix disconnect bases. And then we're going to do the nicks down here. So in this case, there's a 3' end that needs to have a nick after 13 nucleotides. So it's this one. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. In this case, I want the nick to be above the 13th base. So I have to actually select the 14th base when I'm counting backwards from the 3' end, and then do helix disconnect bases to get a fragment here that is 13 nucleotides long. And then likewise, we have to put in our final nick on this strand here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then we select the 14th nucleotide and do helix disconnect bases. So now we can start thinking about bringing these things together and connecting them. So what we could do here is we could probably just connect these ones up even in this state where they're far away, and oxDNA would probably take care of relaxing it without a problem. But we're going to help oxDNA along a little bit, which might be a good idea for more complicated systems, by rotating the helices and bringing them together. So in this case, we want the nicks on the lower helix to be pointing upwards and the nicks on the upper helix to be pointing downwards. So we're going to start by selecting the lower helix now, and we want to make sure that we select the entire helix, so we do it in the outliner. So helix 2 is the lower helix, and then we click E on the keyboard to bring up this rotation menu, and then I'm going to click on this blue line here to rotate it like this. So I just want to rotate it so that the nicks are facing upwards. Okay, that looks good. And then we do the same on helix 1. And now we already have the rotation menu activated, so I selected helix 1 in the outliner. In this case, it's a yellow rotation line. So now we're just going to rotate it so that the nicks are facing downwards in this case. And we can actually connect the nicks up straight away now. So in this case, this purple fragment here needs to Okay, I'm going to click W to get rid of the circles. This purple 3' end needs to connect down here to form the yellow strand in this example. So what I do is I select first the 3' end, and then I hold Shift and click the 5' end I want to connect to, and it needs to be in this order. And then when I have these two selected, I go into Helix, Connect Bases, and they are now connected and forming a strand. And then we're going to connect here, so I select the 3' end, and then Shift click the 5' end I want to connect to, and do Helix, Connect Bases. And then for this nick, we're going to connect this one to this one. So Shift click, Helix, Connect Bases. And then I do select the 3' end, Shift click the 5' end, Helix, Connect Bases. Okay. So what we can do now is just bring the helices together to make it look a bit nicer. So I select Helix 1, and then if I have W on, I get these arrows, and I just move it down so that they are close to each other. But as I said before, it's generally better to have them a little bit too far away than having them a bit too close. I'm just going to leave it like this to have a little bit of safety distance, because oxDNA is going to be able to pull them together quickly. So now we actually have our design done in oxDNA, as far as I can see. So it's always a good idea. Also, I forgot to say this, but it's always a good idea to save many times during your design if you mess something up. So File, Save Scene As will just save the entire working file that you have here. And I'm going to put my example here up on the website vhelix.net, and all the files that I'm creating here I'm just going to upload on vhelix.net if you want to go check them out. So I have them in Documents, Tutorial 1 I call it, and then I'll call this one Tile, and I'll select MA as my format. Continue. So now we are going to export this file to oxDNA for simulation. And there are two ways to get to oxDNA. So one way is to use the TAC oxDNA web converter, but it can be a little bit unreliable for this type of systems. So in my experience, it's safest to use the built-in oxDNA exporter, but that unfortunately only works well on Maya 2019 in Windows as of right now. So you do File, Export All, and then you have a bunch of options here, but what we're going to select is oxDNA top-conf. And I'm going to name this file Tile, and hit Export All. And then it runs really quickly, so that's good. So if we now go into our tutorial folder, we will have saved the 3 files. So tile.conf, tile.top, they are the main oxDNA files, and then there's also a vHelix file that can be used to import the system back into vHelix, but that's quite experimental right now, unfortunately. And what we do now, and it's always a really good idea to do a sanity check to see that your exports looks good. So I do that by using the really good oxDNA viewer. So it's developed by the Peter Solk group in Arizona, and the address is found here, and I'm going to try to add a link to it. So it's just a website, and then you can drag and drop your top and conf file like this. You select one and then control click the other, and you can just drag them straight into the browser and see that it looks as you would expect. So that's always a really good sanity check, because this is what you're going to put into oxDNA. But in this case, it looks good. So I think we can go on with the simulation. So what we need to actually run the simulation is input files. So input files tells oxDNA where to find the files, the top and conf file that describe the system, but also how to run the simulation. So they are just simply text files, and we're going to run the simulation in 3 steps here, starting with what we call input min. So this is the minimization simulation, and I'm going to put these example input files on vhelix.net, so you can just copy them and edit them as you need. So you can just edit them in a text editor, and I think Notepad++ is really good. And then we just see what's in it. So it's just, first is a few program parameters. So it's a backend. So on Windows, we have to run it in CPU. And this first simulation can only be run in the CPU as far as I know. And then it's an important question, how many time steps are we going to run? So for this very first minimization simulation, you're just going to need a number of thousands of time steps. So we're just going to do 10,000 here. And then for this first minimization, as I said, we have sim type min. And then importantly, we have the temperature, which is here 300 Kelvin. And this is important. You want to probably run in the model called DNA2, which is the more modern oxDNA model. And then here's the salt concentration in sodium is 0.5. That's something you might want to change. And then here are the important input and output things. So I'm just going to run everything in the same folder. So, okay, I need to change this. I'm sorry. So the topology file, the top file is just, the name is tile.top and it's the same folder. And then here's where we're going to save the energy. And then the input configuration file is just tile.conf. And then it is the question of where we're going to save the outputs. So the last configuration, we're going to call min.conf. And then we're also going to save a trajectory. So that's just save the state of the simulation as a movie, let's say. Or just save them in a long series. And that we're going to call min_try.dat. And this is an important parameter. This is how often do you want to save to your, let's say, movie. So in this case, we're going to save every 500 time steps. So that's quite a lot of saving. But since this is a very small simulation, it's not going to matter. But if you make larger simulations, these files can become huge. So then you might want to save more sparsely to your trajectory file. So I think that's the most important thing. I'm just going to save it now because I made some small changes. Control S, and I'm going to close it. And now I'm going to bring up the Ubuntu window with oxDNA as we had before. And it's very difficult to see with this blue color where we are. But we are in the oxDNA folder, and we're going to move to the folder where we have the where we actually have these simulation files. So I do, in this case, cd, I can probably type it, so it's /mnt, so it's mount C drive, and then it's users events documents tutorial 1. So this is the folder we have open in here in Explorer. And then we're going to start oxDNA by first giving the path to the oxDNA program that we compiled in the last video. So that's, and then I'm also going to use sudo just to be sure. So we have the permissions to write all the files. So it's sudo /mnt /c /users /events /documents /oxDNA /build /bin /oxDNA. So that's the path to the software. And then we just, since we're already in the folder of where all these tutorial files are, we can just type the name of the input file, which is input min, and then hit enter, and then we need to enter the sudo password. Okay, and now oxDNA is running. So this is just a short minimization simulation that we're going to run first. And it's really quick. And I'm running it because the system is so small, we should say. And I'm running this on quite a weak laptop, but it's working okay for the system. So in this case, it took only 6.5 seconds to run. And then we can see what we got in here. So we got the output files that we expected. So we got the trajectory file, and then the final configuration file at the end of the minimization. So what we can do is we can use the oxDNA viewer to look at these files. So I'm just going to hit refresh to empty the window. And then I'm going to drag in the topology file that's never going to change here. So it's tile.topology, and then the control click min_try.dat, and then just drag it in. And what we can do is we can use the back and forward error the right and the left arrow on the keyboard to just move through the trajectory and see what's happened in the simulation. So it's sort of tightened the simulation up, and it's removed any possible overlaps that may have been in the file, and this is just a good visual inspection. And if it still doesn't look good, you might have to run more steps of this, like this, but it looks good to me. So what we're going to do now is move on to the next type of simulation, which is the relaxation. So then we're going to move into input relax, and I'm just going to edit this in text editor. And this one could be run on a GPU if you have one, and if you're running Linux, but we're going to run it on backend CPU again. And now we're actually going to do a molecular dynamics simulation, and we're going to do it in this case for 100,000 time steps. But what's important to mention here is that we have the max backbone force activated here, and that means that it's not a real oxDNA model, but it has a truncation of the amount of forces that you can get between bonded backbones. So that's really good for pulling things together. So in this case, the two helices may still be a bit too far away, so that's why we do this relaxation, to get into a really good state where we can run the real oxDNA simulation a bit later. So I'm going to run 100,000 steps, and I'm going to save to the trajectory every 1,000 steps, which risks creating quite a large file, but it's nice because we can it makes the simulation trajectory more continuous. And the input file here is the same topology as last time, but the configuration file is actually the end file of the minimization simulation. So that's where it's going to start doing its thing. So in this case, I don't have to change anything, so I'm just going to close it. I'm going to bring up the Ubuntu window again. And then I hit the up arrow to bring up what we put in last time, which is just the path to the oxDNA software. And then I'm going to change the input file to input relax, and then hit enter. And now I didn't have to and now I don't have to hit the sudo password because it's already been entered before. Alright, so now the simulation has finished, and on my relatively weak laptop that took 73 seconds. So what we can do now is we can look at the relaxation simulation just to see how it looks. So we are gonna bring up the Ox viewer again and refresh it to remove our old file. And then we can go into the tutorial folder, and we can see that we have created a relax.com file, which is the last state of the relaxation simulation, and then a trajectory file, which is the whole simulation. So I select the trajectory file and then control click tile.top again and just drag them both in. And now again we have a movie where we can use the left and right arrow keys to move through the simulation movie. And now we can see that this probably relaxed pretty quickly to pull the backbones together. So this simulation in this case might have been a bit longer than we needed, but for larger structures like origamis you might need much longer relaxation simulations than we have here. So the easiest way to check this, or one way to check it, is to just go in to try to run the real simulation, and if two backbones are too far away, it's going to crash and tell you that you need to relax the structure more. Okay, so this is the relaxation simulation. Now we're going to move on and do the real oxDNA simulation without any constraints on the backbone force. So to do that, I have a third input file that I call input go. Just going to open it in the notepad again. And this is quite similar to the last input file, but the difference is we don't have any max backbone force, so we're running with the standard oxDNA backbone potential. And the input file here is the same topology file as always, but the configuration file is the configuration from the relaxation simulation. And here I'm also going to run 100,000 steps and save every 1,000 steps, but you can run it for as long as you want, as you're interested in trying to simulate. So again, to simulate this, we bring up our little Ubuntu window, and we just hit the up arrow to bring up the path again to the oxDNA file, and then we change input relax to input go and hit enter. And now we've started the oxDNA simulation. So This should take roughly as long a time as the last one. Alright, now the simulation has finished on my computer, and on my laptop this took around 70 seconds to run. And now we can just go into the oxDNA viewer again to see what we have. So we just hit refresh to empty it, and then we go into tutorial 1, select, and now we see the new files we have is simp.conf, which is the final configuration state at the end of simulation, and then this trajectory file here, simtry.dat. So we do simtry.dat and tile.top, and we drag it into the oxview. Now we can use the left arrow to look through our actual oxDNA simulation. So even just running it for a few minutes on a laptop can tell you quite a lot about the 3D shape of a small system like this. So that's it for this video, and I hope this was useful to you. And I will upload the files the input files that I use in this file, and also my saved files, to a zip folder on the website vhelix.net if you want to find them. And so thank you for watching. Bye bye.